Swayam Prabha. Digital India. Educated India.
So that's the case I am considering. In this case, lambda 1 is 25 and lambda 2 equal to 0. So there will not be any y2 square term there, because lambda 2 was the coefficient of y2 square. There is no y2 square. There is just y1 square, and then there is y1 and there is y2, etc. So that equation will represent ellipse. Yeah. So put a equal to 1 over 5, because the eigen we have to write down orthonormal basis of R2 to find our matrix U of change of coordinates. This is the matrix, orthogonal matrix for change of coordinates, and the equation are x1 x2 equal to U y1 y2. I know U, so I can write x1 and x2 in terms of y1 y2. These are the equation of x1 and x2 in terms of y1 y2, and the equation in the y1 y2 plane is simply y1 square plus y2 equal to 0. Very simple equation has come. Yeah. So in the y1 y2 plane, this represents a parabola, right? This represents a parabola. So y2 is always negative. Y2 equal to minus y1 square. So this represents a parabola of this shape in the y1 y2 coordinates, and y1 y2 coordinates have been obtained by multiplying x1 x2 by U inverse. U is orthogonal matrix, and U in this case the determinant of this U. What is the determinant of U? Let's find out. The eigenvalues and eigenvectors. Eigenvalues were these: lambda 1 equal to 25, lambda equal to 0. So so the original matrix, determinant of this matrix is product of eigenvalues. So this is this matrix, yeah, is not invertible. As you see, the determinant of this matrix is 16 times 9 minus 12 square, and that is 0. So it's a determinant 0 matrix, and so that has reflected in one eigenvalue being 0. Yeah, for the case of ellipse and hyperbola, determinant was not 0. It was, when it was positive, then it will give rise to ellipse. When it is negative, it will give rise to a hyperbola, and when it is 0, it is giving us a parabola. So the nature of eigenvalues, what are their signs, whether one of them is vanishing or not, they have effect on the shape of the equation. Yeah. Okay. So now let us move to dimension 3. So we understand how to determine the shape of an equation which is represented by a quadratic equation. So we just focused on quadratic part, wrote the real symmetric matrix, found out its eigenvalues and eigenvectors, and that removed the mixed term, and then we did some translation of axes, and then we can determine the shape. And the shape was being controlled by the nature of the eigenvalues. So if A is invertible matrix, then determinant of A could be positive or negative. If it was negative, it represented a hyperbola. If determinant was positive, it represented a ellipse. When determinant is 0, it represented a parabola. Okay, so let us now go into dimension 3. In dimension 3, the surfaces which are given by quadratic equation, and you have seen such surfaces in calculus like ellipsoid or sphere in dimension 3, or hyperboloid of one sheet, or hyperboloid of two sheets, okay, or parabolic hyperboloid or hyperbolic paraboloid, and there are all kinds of surfaces which are represented by quadratic equations in dimension 3. The possibilities become much more. Okay, let us apply the same procedure. We will diagonalize a quadratic form in 3 variables now, okay, by using a real symmetric matrix. So quadratic surface is the locus. It is the locus in R3 of the following equation. Yeah? There are degree 2 terms, pure terms, there are mixed terms, and then there are linear terms. Okay, this is the most general quadratic equation in three variables, and we want to understand what surface it represents. Yeah, what surface it represents. So for example, x square plus y square plus z square equal to 1. This is the equation of a sphere. If you write x square over 4 plus y square over 9 plus z square equal to 1, this is an ellipsoid. Okay, this is an ellipsoid. Or x square plus y square equal to z square. Yeah, what does this represent? X square plus y square equal to z square. So if I fix a value of z, it is a circle. So if I cut this surface with a plane which is parallel to xy plane, I will keep on getting circles. Okay, the cross section of this surface with planes which are parallel to the xy plane at various heights are all circles, and the radii of these circles are increasing as z is increasing. When z equal to 0 is a point. When z is very small, it's a small circle. But it is in z equal to some plane, parallel to plane. So we get these circles, and this is the surface. Okay, this is the surface. Right? So many kinds of surfaces are possible, which are represented by quadratic equation. Now when I have written this equation, I can assume that not all three are negative. If all three are negative, I can multiply in by -1 sign, okay, and get all three of them to be positive. Okay, so not all three are negative in this case. So A and B could be positive, C can be negative, or A is positive, B and C are negative. Such possibilities are allowed, but at least one of them is positive. Yeah, we can always do that, right? So terms of the second degree, look at the terms of the second degree, this part and this part. These are the terms of second degree. These are the terms of second degree, and we want to now diagonalize, write in matrix form. Okay, this is the quadratic form. It determines, this quadratic part will determine the type of quadratic surface. The real symmetric matrix associated with this quadratic form is going to be 3 by 3 now. Yeah, because these diagonal terms will be ABC, and then xy coordinate. I mean these are the other three terms there. Okay, so A, B, C, these are the quadratic terms. Then xy. Okay, A prime over 2 is xy. Okay, so this represents x, this represents y, this represents z, and this represents x row, y row, and z row. Okay, so A prime over 2 will be the term which is going with xy. Yeah, this is A prime. So I divide by A prime, divide by 2, and matrix is symmetric, so I put here. This is corresponding to xz. Okay, xz is C prime. So I have to put C prime over 2 here, C prime 2 over here. This is corresponding to yz. Yz has a coefficient b prime, so I put b prime over 2, b prime. Right? So the three columns and three rows correspond to these three variables, and I can write down the entries of this matrix, and I have to make sure that it is real symmetric. So the coefficient of xy, yz, zx, they are divided by 2. Okay, that is the real symmetric matrix, and the original equation can be written as xyz times the real symmetric matrix, column vector xyz, and the linear part is written like this. Linear part, I can write a double prime x plus b double prime y plus c double prime z, and this is a constant term. We did the same thing for quadratic forms, quadratic equation in two variables. Now we are doing the same thing for three variables, writing it in matrix form. Okay, we are writing it in matrix form. All right, so this is the matrix form, and we can diagonalize the real symmetric matrix. This is now a 3 by 3 matrix. The characteristic equation will be a cubic equation involving the entries of A, B, C. But let us say we have found the eigenvalues of this real symmetric matrix and the corresponding orthonormal basis of eigenvectors. And the D is the diagonal matrix where diagonal entries are eigenvalues, and change of coordinates is same, x equal to C UVW, where C is the matrix of eigenvectors, orthonormal basis of eigenvectors. So this is the change of coordinates. So I can write x, y, z as linear equations in u v w by looking at this equation and go back and substitute. So the quadratic part was x, y, z, a times x, y, z transpose, but a is equal to c transpose ac. Okay, a is equal to no, it should have been x, y, z. Now it is fine. So C times U, wait a minute. Yeah, no, this is fine. All right. Okay, so I have just put XYZ, sorry, XYZ is equal to C times UVW. So I have not changed A here. I have written XYZ is equal to C times UVW. Okay, so then I get this equation, XYZ is C times UVW, and this is the transpose. Okay, this is the transpose, but this is the transpose of this column vector. Okay, this is, I got confused. This is a column vector and this is the transpose. And we are writing x equal to CU, this UVW. Okay, UVW. This is the new coordinate system, UVW. So when you substitute this, the matrix get diagonalized. C transpose AC becomes diagonal matrix because column vectors of C are eigenvectors of A. Okay, and D becomes diagonal matrix. Diagonal entries are lambda 1, lambda 2, lambda 3. So this is the quadratic form in UVW corresponding to the diagonal matrix D of eigenvalues. So QXYZ is equal to QD UVW by change of coordinates. Okay, and the original equation can be now written in terms of UVW. Okay, the quadratic part becomes this, and this is the linear part, x equal to C times U plus D equal to 0. So that's the equation in UVW. Okay, and then you can work it out. Okay, so just like in case of two variables, a quadratic equation can represent empty set, it can represent a pair of lines, it can represent one line repeated, or it can represent an ellipse or hyperbola or parabola. So these were the 6 classifications. Similarly, for quadratic equations in 3 variables, we have a classification. So there are some degenerate cases like empty set or 3 distinct lines or 2 lines or 1 line, and then there are other shapes. So these are the primary cases which are non-degenerate. Okay, so when all 3 eigenvalues are positive, then we get ellipsoid. Just like when both the eigenvalues were positive in case of 2 variables, we got ellipse, but now we will get ellipsoid. When 2 are positive and 1 is 0, then we will get elliptic paraboloid. Okay, the equation will become like this. Then when 2 are positive and 1 is negative, 2 eigenvalues are positive and 1 is negative, we will get an elliptic cone. Okay, this is an equation of elliptic cone. That's the name. When 2 are positive and 1 is negative, then we get a hyperboloid of 1 sheet. Okay, 1 sheet corresponding to 1 negative eigenvalue. When 2 eigenvalues are negative and 1 is positive, I get 2 sheeted hyperboloid. Okay, when 1 is positive and 1 is negative and 1 is 0, then I don't get all 3 quadratic term, I get a linear term, and this is hyperbolic paraboloid. Okay, so 1, 2, 3, 4, but there are 6 non-degenerate cases, and there will be several degenerate cases where we don't get such shapes. So that is the classification of quadratic surfaces. Yeah, so let us look at some examples. So consider a quadratic surface which is given by x square plus y square plus z square plus 4xy plus 4yz minus 4zx minus 27 equal to 0. Okay, so it has these mixed terms. It is not clear what it represents. Okay, it's not clear what it represents. So first look at the quadratic part and write the quadratic form, which is part of this equation, and then write the matrix of this quadratic form. Coefficient of x square, y square, z square are 1. So I get this 1 on the diagonal, and then look at the coefficient of xy, that is 4. So 4 is divided into 2. I get these 2. Coefficient of xz is minus 4. Divide by 2, I get minus 2 minus 2. Coefficient of yz is 4. Divide by 2, I get 2. So this is the real symmetric matrix, which is representing this quadratic form, and I can write down the eigenvalues and eigenvectors of this. They turn out to be 3, 3, minus 3, and the related quadratic form is this. That's the related quadratic form. Okay. So here I'm writing change of, I am not writing xi, y, ui, etc. So we have original coordinates are x, y, z. The new coordinates are u, v, w. Okay. And the eigenvalues are 3, 3, minus 3, and u. Therefore, if I write x, y, z, x, y, z, this is the change of coordinates. The change of coordinates is given by x equal to uy. So u, v, w. Okay, that is the change of coordinates, and so I have to find out what the eigenvectors are. Okay, and so when you substitute, then you can write v and w in terms of x, y, z. Okay, yeah, by inverting the matrix or taking u transpose. So under this change of coordinates, when you do that, then the quadratic surface becomes this. And this is equation of a one-sheeted hyperboloid. You can draw this shape. You have seen this. This is one-sheeted hyperboloid, and the unit vectors along u, v, and w axis will be the eigenvectors. u1, u2, u3. These are the three eigenvectors. These are the directions of the axis with respect to the old coordinates. These are the coordinates of the orthonormal basis, which is representing the new coordinate system, but we are writing in the old coordinates. Yeah. So these are three mutually perpendicular directions in the three-dimensional space, and I know the coordinates of the tips of these three vectors, and these are in the directions of these. Okay, this is v, this is u, and this is w. If you draw these, that's so, and the shape is, remember the equation. Equation was u square plus v square equal to 9 plus w square. Okay, u square plus v square equal to 9 plus w square. Yeah, so if I put w equal to 0, then I get an equation of a circle of radius 3 in the uv plane. This is the uv plane, and this is the equation of a circle of radius 3 centered at the origin. As I move in the positive y w axis or negative w axis, the radius of the circles, which are sections of this hyperboloid with the planes which are parallel to uv plane, those radii become bigger and bigger. As w becomes bigger and bigger, I get circles of bigger and bigger radius. Okay, so I get a hyperboloid. Why it is a hyperboloid? Where is the hyperbola in this equation? Well, the hyperbola in this equation is put v equal to 0, then I get u square minus w square equal to 9. So if I cut it with planes which are parallel to the WU plane, I am putting various values of V. When I put various values of V, so in particular I put V equal to 0. So the UW plane is represented by V equal to 0, and that is going to intersect my hyperboloid in this hyperbola, U square minus W square equal to 9. Okay, right? So that's why it is called hyperboloid of one sheet. It is a connected surface. You can get equations which are hyperbola two sheets, but they are represented by two negative eigenvalues and one positive eigenvalue. Okay, yeah, you will get paraboloids, etc., when one of the eigenvalues is 0. Okay, so these are the applications to analytic geometry